really what I want to talk about today is really about statistical thinking and how it's important for day-to-day AI. But before I start, let's think a bit about the successes of AI, generating images or text. We use language models a lot, understanding voice. I've been talking a lot to my computer lately, proving theorems. And the question, you might ask is what do statistical tool have to do with this, especially, for instance, proving theorems, because this is all basically formal statements. There is no noise. It's all deterministic. So why do we need statistics there? Well, if we take a step back and we think of the big picture, a lot of the modern developments in AI are about finding continuities, about enabling interpolation and extrapolation, leveraging similarities. If we think we know what Timothy just discussed, it's my hypothesis is that it's partly driven by extrapolating from known proofs, which is probably not very different from how we work as humans. And extrapolating or interpolation is much easier when you have continuous representations. So really what most of those tools are going to do is that they're going to embed discrete objects, they're going to embed symbols, they're going to embed logic, and put them in a continuous space, which then allows for mathematical reasons to build much more easily predictive functions that basically extrapolate through the commonalities between the objects. And where do we have uncertainty in this? Well, sometimes it comes from incomplete problem description. So, for instance, if you're learning to play Go, you don't know what your opponent is going to do. So you might consider this as uncertainty and tackle it with a randomness, and so have a statistical twist to it. Another aspect is that ignoring some of the details helps generalizing, and sometimes actually it's well known in statistics that accepting some error is useful. I should say it's well known in statistical learning, so in machine learning. And then, even when things are not random in any way, real life is full of ambiguities, ambiguous stimulus, like the one I'm showing here. When we think about language models, we're dealing with symbols, we're dealing with text, but those symbols take their meaning only thanks to context. For instance, the word bank can mean a river bank or a bank where there is money, like Bank of America. And you can only know the difference between those two given the context. So there's a null point of view, which is that we're going to work on disambiguation. We're going to work on assigning clear symbolic meaning to every word. But it can only go so far. Think about this sentence. Fruit flies like a banana. It can mean two things. I could be talking about fruit flies or about the fact that a fruit is flying like a banana. And the sentence is valid in both meanings. So I personally don't believe that logic, curation, normalizations, rules will suffice to model our world, because our world is full of ambiguities, full of uncertainty. And then there's a well-known problem, is that when we slap categories on our world, we end up shaping the world. So for instance, here I've put a list of terms related to academic titles, early, mid-level careers in different languages and so different countries. And if you're trying to make link between these, you simply cannot, because the systems are different. And so well-known challenge of socio-technological systems is that when we build categories in socio-technological systems, we build categories in how we register employment, we describe people, we're shaping the world because the world needs to conform to these categories, and because these categories also ground our measurements. So it's been well described, for instance, by Alain Desrosières, who is both a statistician and a sociologist. So language models, which we've seen powering today's AI revolution, actually go across these problems. They build a consistent view without having to align references or schemas. They can compile contradictory information. They can even bridge non-quantified cultural uncertainties. And one of the challenges that they address is basically forcing a huge amount of knowledge into finite size representation with continuous embedding. And that creates a compression, and it's a lossy compression. And in terms of understanding the world, lossy compression is well documented as being a good thing. So as a consequence, they have errors. For instance, if I asked, that was a little while ago, if I were to ask an AI system to tell me something about Albert Einstein, it would tell me things that look correct, but here it's telling me that Einstein submitted a PhD dissertation to the Humboldt University of Berlin, which I know is not true. So we'd like some form of confidence to come with these statements. So we'd like to be able to label, confidence on different parts. And a classic way of doing this is to monitor the error rate of AI systems and ask them to give some form of confidence in their output, and then monitor, consider this predicted confidence as a predicted probability and monitor the corresponding error rates. And so then we can do bins on this, and then we estimate probabilities by counting how many times the AI system, it could be an LLM, it could be anything, is correct when it claims it's correct 70% of the time. That's known as calibration. I'll go back to it. So we can do a calibration curve, and we see that here an LLM is typically overconfident. It thinks it's right more often than it is. Now, the point being that calibration is not enough. Calibration is not a fully well-controlled statistical measure. And we can see it, for instance, if we vary the query nationality, so on the type of questions that I've been asking, what you can see is that an LLM is going to be well calibrated much more often on, for instance, individuals from the US or other Western cultures rather than individuals from China or India. And the reason is because these LLMs were trained on data that is more precise, richer for Western cultures than for Eastern cultures. But the point I'm trying to make here is that calibration is not enough. We would need a full statistical validation of the LLMs, and some people are doing this. Okay. So what I was trying to drive through here is that statistics are important for AI, even on topics that seem to come with certainty. I say seem to come because if you're talking about world knowledge, there are lots of cultural uncertainties, there are lots of ambiguities. Even world knowledge can be considered as with uncertainty. And so now I'd like to talk a bit about what I call data science and how it relates to AI. Really, data science is about building some form of process from empirical evidence. And the tool I personally use for this is machine learning because it can automate problems we don't know much about. And I've been doing this for a little while, and it's been applied to many, many problems everywhere, and problems that are often very important to our day-to-day life. Things like optimizing an industrial process or detecting credit card fraud. So machine learning is absolutely everywhere. And I really think the right tool, conceptual tool to think of it is, once again, statistics. And it's if you do academic studies of machine learning, you do it using statistical tools. And so the formal problem that we're tackling here is that we're given data that we typically call X and outputs that we typically call Y. And what the machine learning, what we call a predictor, is doing is to learn a function that goes from x to y such that f of x is close to y. And typically, the problem that we're solving is that f of x is estimating the conditional expectation of y given x. That's what we do when we minimize a quadratic loss. Okay, so maybe I'm putting too much mathematical jargon, but really, maybe a way of thinking about this is that we have noisy data and we're estimating the mean of the output for a given input. The challenge being that we don't have a lot of data, we only have very few points, and so that mean, that's conditional expectation, is difficult to estimate. That's really the problem that machine learning is tackling, and that's the root of everything, including LLMs. Okay, I'm a bit short on time, so I'm going to skip a bit some aspects of this. And so the theory tells us that if we have a very flexible model and we have a lot of data, the model is going to converge to this conditional expectation. So naively, we could think, powerful models and big data are all we need. But in real life, we typically don't have the right data. So we typically have a data or source data that differs from a target data. In some settings, the link between X and Y is preserved. And so if the target domain is covered, then in such a setting, which is known as a covariate shift setting, all I need is indeed a very flexible model and a lot of data. But often I have selection bias on a common mechanism of X and Y. This is an example. My orange cloud of point is a subset of my blue cloud of point. The association between X and Y is changed here. So asymptotically, more data flexible models will not fix it. So one example is that of reasoning on models for intervention. So suppose I'm interested in health. I'm predicting a health outcome from different health covariates. And I would like to know whether, using this predictor, whether it's useful to assign a treatment or not. So for this, I can contrast the prediction of the model, should I give the treatment, versus the prediction of the model, should I not give the treatment. However, the challenge is that the people who are not sick didn't get the treatment in the data I've seen, and the people who are sick got the treatment. And so one problem is that models are always doing simplifying assumptions, and so the model can basically capture this and associate the treatment to negative health outcome. This is known as confounding. And something that is not obvious is that a simpler predictor that predicts less well on the observed data may be able to extrapolate better. So what I'm telling you here is that how you evaluate a model depends on how you're going to use it. So the kind of questions that I asked are questions that are underlying day-to-day applications of data science. It's not only about predicting from IID data, we need to think about how we are going to use the models. And here, validation is a bottleneck. So, as you probably all know, to validate, we can only validate those models on unseen data. Elsewhere, the only thing they would do is basically memorize the data and not be able to generalize. Then there are important questions on what is the validation metric that we're going to use. There are two ways forward. One is to try to control probabilities, and we're going to do this using what's known as proper scoring rules, such as Brier score, which is basically the error between the predicted confidence and the observed binary labels, or we're going to cause the problem and understand the value of how we're going to use the prediction and validate the models by their value. And here this is challenging because all the metrics that we're using are imperfect views on utility. And I'd like to stress that choosing the right metric is as important as choosing the right model. And what post-mortem evaluations of industry problems tell us is that those evaluations are always imperfect because we're typically, for instance, optimizing proxies of our value of interest, and we end up over-optimizing those proxies. Or when we're deploying the models, the effect, the model predictions are actually going to change the system. So the system is going to change as we deploy the model, and that is related to the causal problems I was mentioning before. So for this reason, my team and I at Probabl have been developing a library that we call SCORE that really focuses only on model evaluation, and I will not describe it today. I don't have time. It comes with Python-based interface close to scikit-learn that we all love, but it also comes with an online hub that we feel is extremely important to bridge in non-technical stakeholders, because finding the right validation comes with bridging non-technical stakeholders. All right, I'm going to stop here. I hope that I was able to convince you that statistical thinking is crucial both for AI and data science and the intersection. Thank you very much.